Okay, question 12. We're on to mechanics. In physics, a conservative force is one for which A. Kinetic energy is conserved, B. Potential energy is conserved, C. The change in energy depends upon the path taken, D. There is no dissipation, E. The acceleration is always in the direction of the force. Well, the answer is D. There's no dissipation. Okay. Kinetic energy is conserved. No, kinetic energy changes with a conservative force. When you drop something, gravity is a conservative force, but the kinetic energy of something in a gravitational field can change. Potential energy, same deal. Gravity is a conservative force. Drop something in a gravitational field, its potential energy changes. The change in energy depends on the path taken. No, that's exactly the opposite of a conservative force. A conservative force is where the change in energy does not depend on the path taken. And E, the acceleration is always in the direction of the force. Well, the acceleration is always in the direction of the net force, whether that force is a conservative force like electrostatic force or friction. It doesn't make any difference. So D is the only one that makes sense. All right. Now we've got a train consists of a locomotive, Thomas, pulling trucks Annie and Clarabelle on level ground as shown in the diagram below. There they are. So Thomas is pulling. The type of coupling attaching Thomas to Annie and Annie to Clarabelle, that's this, Thomas to Annie and Annie to Clarabelle, can withstand a tension of 3 by 10 to the 4th newtons before it breaks. What is the maximum rate at which Thomas can accelerate the train before one of the couplings breaks? Ignore rotational motion of the wheels and it not shown in any friction. Okay, so this one is nice and straightforward. So if we have an acceleration A, then the force required to create it is m times A. So if Thomas here accelerates at a particular rate, this coupling here is responsible for providing enough force to accelerate both Clarabelle and Annie. That is, the mass it's accelerating is 30 tons, which is 30 times 10 cubed kilograms. Okay, this one here, on the other hand, is only supplying enough force to accelerate Clarabelle. So it's only accelerating 10 tons, so it doesn't have to be as strong as this one here. There's no one out here where all three are being pulled, so it's only these two are being pulled. So if we rearrange, we get A equals F over M, and our tension, the force that this coupling can supply, the maximum is 3 by 10 to the 4th newtons, divided by the mass, which as I said is this one, is strangely enough 3 by 10 to the 4th kilograms. So the acceleration is 1 meters per second only. This is squared. So B is the answer. Okay. You might have chosen D if you thought that there was a coupling here pulling all three, but that's not the case. No, actually no, that would have been A, wouldn't it? If you thought there was a coupling that was pulling all three, you would have chosen A. You would have chosen D if you thought that this coupling only needed to accelerate Annie and didn't realize that it needs to supply enough force to accelerate both of them. And you could have chosen E if you thought that this coupling was the one that was doing all the work and it just had to support Clarabelle, whereas that was the one under greater pressure, tension. And now for the weirdest question. Energy is normally quoted in joules. Which one of the following is not an equivalent set of units? And all of them are equivalent. Well, let's see. Kilograms, what's a joule? A joule is, well, I always think it was a Newton meter, so that's kilogram metre second to the minus 2 times metres, so it's really metres squared. So kilogram metre squared second to the minus 2. So that's equivalent. Newton metre, that's equivalent of course. The watt is the rate at which you do work. So the watt is power joules per second. So joules per second times seconds is going to be joules. And pascals times metre cubed, well that's pressure times volume. And as we all know, that's joules as well. Because in heat and thermo it's joules, and so it's joules in mechanics too. Can we, I can show it explicitly if you like. Pascal is Newton per metre squared, and volume is metres cubed, so we get it cross cross, and that just turns out to be Newton metres, which of course is joules. So all of them are equivalent, and A is the answer. And we tricked you by putting one out of context there, so you would think it's that one. I didn't know that would trick you. Ralph must have known, he put the question in. So here we have a system where we have an inclined plane. It has a box slides down a ramp, so it's sliding down initially, and because of friction it slows and eventually stops. Okay, so after a while it just stops dead. And the question is, if the coefficient of kinetic friction between the ramp and the box is mu, then the distance it will travel along the ramp before coming to rest is, and you've got to try and work it out. Okay, so a couple of clues, and let's see if we can solve it without doing any real work. It would be better if we could. So first of all, if it's flat, if theta is equal to 0, so it's just flat, then how long will it go? Well, if theta is equal to 0, then you have the box is sitting here like this. It has a normal force, normal equals to mg, and so therefore the frictional force is equal to mu mg. Therefore, the work done by the frictional force is going to be equal to the friction force times the distance it takes to stop, and this must be equal to the total amount of energy lost, which is a half mv squared. So we have mu mg times d equals a half mv squared. So we have the distance is equal to, the masses cancel out, the distance is equal to v squared over 2 mu g. Okay, so if for the case of theta equals 0, any answer we get must reduce to this. So let's look at these starting at the bottom. This is v squared over 2g mu cos theta plus sine theta. So cos of 0 is 1. Okay, so this one will work, okay, because sine of theta is 0. So this reduces for theta equals 0 to mu squared over 2g mu, v squared over 2g mu. So that one could be. This one, no, it's got a v on the bottom. This one, no, it's got a v squared on the bottom. This one's got a v squared on the top, but it's got a tan theta on the bottom, which means that tan theta is 0 for theta equals 0, which means it'll be infinite. It does not reduce to that, so that's wrong. And this one is rather like this one. It's 2g mu cos theta, which is, that's 1, minus sine theta. So this one is also possible. So the others are ruled out because they're just all wrong. And these two are possible. Now, let's have a look at this. As we raise this slope, the distance it takes to stop should get longer, shouldn't it? Because you think we are gradually increasing. Okay, and at some point, for a certain amount of friction, at some point, you should get a case where the stopping distance is infinite. Why? Because there's going to be a slope, provided the friction's not too big. There'll be a slope where it'll just slide at constant speed. It'll never stop. Okay? So, does one of these give us a situation where the thing just slides and doesn't stop? And the answer is this one does. Because this one, when mu cos theta minus sine theta is 0, will give us an infinite stopping distance. This one, for angles between 0 and 90 degrees, which is all we're concerned about, this one will never give us an infinite stopping distance because that's positive and that's positive. So it won't give us an infinite stopping distance. So this is the actual realistic one, and that one's not. You can, if you want, actually do the analysis. It's not hard. You just have to work out, right, there is mg. It's got a component there and there. This one being mg cos theta. This one being mg sine theta. The frictional force is going to be, if we draw the normal force there, mg cos theta, then we're going to have the frictional force is equal to mu mg cos theta, and the gravitational force is going to be mg sine theta. So the acceleration, or the total force, the sum of the forces acting just in this direction, is going to be mg sine theta minus mu mg cos theta. So therefore the acceleration is going to be g sine theta minus mu g cos theta, and so therefore the stopping distance using v squared is equal to 2ax. Therefore we're going to have 2 times ax equals v squared, 2 times g sine theta minus mu g cos theta times x equals v squared, and so you get an x, the distance is v squared over 2 g sine theta minus mu g cos theta. I realise I'm writing where you can't see, so I'll move that up. And that is that, except the signs are the wrong way round. And of course that's because there's two situations. There's the situation where the thing slides and slows down to a stop, or if it's too steep, where the thing slides and gets faster and faster. And so changing these around is not a problem, but that's going to be the answer. Okay.